Welcome to Chemistry with Crip. We're going to take a number of models that you would have had available to you in the classroom, and we're going to analyze them according to our sigma and pi bonding as well as a bit of geometry. So let's begin with actually these guys over here. So this is called alkane. Alkane has got an alkane. We call this specifically ethane. Eth means two. So you have two carbons atoms in the structure, and we've got 6 hydrogens. And if you can see, the most stable configuration would actually be those hydrogens alternating. But the structure can actually freely rotate, and that's one key distinction with having just sigma bonds, is that the orbitals can actually freely rotate around each other. So it's possible to have a more stable configuration, right, and a less stable configuration when they're kind of lined up and repelling each other, those fields. Now we can compare that to, say, something like ethene, in which you have 2 carbon atoms, but now they are double bonded to each other. And so what's a double bond? It's a sigma bond as well as a pi bond. So this right here is representing our p orbital on this carbon, and this right here is representing our p orbital on this carbon. And of course, them making this connection forms our pi bond, and that's above and below the sigma. And you can see in this case, these cannot freely rotate, okay? You would actually have to break the pi bond in order for them to be able to freely rotate. And so this is an important takeaway from this unit, being able to describe the properties of the actual structure. Let's take now our ethine. Okay, let me line this up so that it's correctly. So there we go. This is just indicating the positive value on the y-axis. And if you can see there's the positive value on the z-axis coming out. So here we have a triple bond, because there's a sigma bond in the center. Above and below, we've got a pi. And another, before and behind, we've got another pi bond. And so you can now see we only have 2 hydrogens. But this would be extremely resistant to any kind of possible rotation. So let's put those over there, and let's bring our smaller models, because they're kind of convenient to talk about. So here we have, in our structure, right, we've got ethene again. And you can imagine the pi bond. I like these smaller structures because we can represent the pi bond just by simply putting our fingers across, right, the 2 carbons. And we can easily see that those hydrogens cannot, you can never have a possible example like that. Absolutely not. That would never happen. You need them such in that position, because those p orbitals need to overlap each other, and so that's going to force those hydrogens to actually be perpendicular to that p orbital, to the pi bond. So you can see that structure right there. Notice how we can actually have, notice this is a little bit different color, but that's fine, it's still carbon. Here we have 3 carbon atoms. If we have a pi bond over here, and we have another pi bond over here, the pi bonds themselves would have to be perpendicular to each other, because this carbon atom, the central carbon atom, would actually have to use 2 different p orbitals to bond with the other carbons. So you can imagine kind of on the y-axis with this carbon, and then on the z-axis with the other carbon. Continuing on, let's bring in biacetyl. So here we've got a number of, I'll bring that a little closer, a number of double bonds. So 2 double bonds here, 1 double bond here, 1 double bond here. And again, you might think that they cannot rotate, but of course there's just a sigma bond in the center, so there's quite a bit of free rotation about that sigma bond. Of course, you could also have some rotation over here with the 2 other sigma bonds where they're present. It's important to be able to recognize that and envision that in the structure. Let's see, acetylene. Again, the only double bond present is right here, so that's the only thing that would not be able to freely rotate. Everything else would be able to freely rotate in the structure. If we take something like acrylonitrile, there's the next one there, acrylonitrile. If we look here, carbon is triple bonded to this nitrogen, and we've got a double bond between these 2 carbon atoms right here. So you can see that actually the structure wouldn't be able to change much. The only place of free rotation is that sigma bond, but that doesn't really change the structure much at all, right? So yeah, let's see, methacrylate, right? Again, we're looking for the places where there's pi bonding that would make those structures around that axis fixed. So again, here and here, but everywhere else in the structure where there's sigma bonds, again represented by these kind of clear things right here, there would be places of free rotation, right? And in the structure, as you can see, the gray ones are really representing the double bond, where you have the presence of a pi bond. Continuing on to the next page, you've got a number of structures. There's AZT, there's heparin, right? And of course, if you were in class, you'd be strongly encouraged to actually play with these models, because in order to see the difference in hybridization and the kind of electron geometry that you see represented here, right? You can see that some of these are existing in the same plane and some of these are not. So you can see like that part over here, this ring structure, they're kind of going above and below. And there's an important reason for that, because those carbon atoms, each carbon atom, right, and the oxygen is sp3 hybridized. So you're expecting a geometry that's tetrahedral. And so they're going to kind of go up and down out of the kind of the plane of reference. If you compare that to heparin and capsaicin, both of those have these hexagonal ring structures. You can see right here, and this is alternating double bond, single bond in the structure. So because of that, the hybridization of each of these carbons is sp2 hybridized, and it will exist as trigonal planar. And so when you have all 6 of them having that, notice they all exist in the same plane because they're all trigonal planar. And you can see that's heparin. That was heparin. This is capsaicin. And capsaicin is having a similar ring structure as well. They have this kind of similar end because they activate similar receptors, pain receptors on your tongue when you consume them. Let's see. So a big takeaway here is how important pi bonding is, because if we take a structure like this guy, you see that on the last page, right, and compare it to this guy, they are completely different chemicals. Of course, we could easily turn them one into the other, right? But we would need to break the pi bond, right? So right now there's a pi bond that's fixed in place. If we break the pi bond, this can twist and we can have that. And really there's only 2 conformations here. Either we have this conformation or this conformation, but they are not the same substance. You have to break a bond in order to form the other. And then lastly, we have some substances at the end, right? You can see here's carbon monoxide, and that would be triple bonded if you draw that correctly. And then here we have carbon dioxide. Of course, that central carbon would have to have 2 different p orbitals in which they're forming the pi bonds. Here's an outrageous scenario then. Here we can imagine p orbital being there, p orbital being here, and then p orbital being here, as well as the p orbital being here, in which they're all double bonded to each other. Till next time, Crip.